Okay, now it's done. We can start.
Okay, so I just turn off my video. Okay. Let's start today's lecture by giving you. Let me start this lecture by giving you some references to exposition or expository or survey papers on spherical varieties. Here is a list. So the first one is an expository paper by Michel Brion. It's quite old, more than 20 years ago, almost 30 years ago. But still it is relevant. It's a good basic exposition of the theory. The only problem is that it is in French. So it is a preprint of some lecture course on a summer school. It is, well, I even don't know if it is published, but at least it is not published in some journal. Maybe some notes of summer school. I don't know. But this paper is available on Michel Brion's webpage in the University of Grenoble. This is the link. The only problem with this paper is that it is in French. So if you read French, then you can use this source. If not, then unfortunately you can't. But there are other papers in English. They are more of survey type, so not like textbooks, but rather surveys with less proofs, some proofs omitted, more references given, and so on. So the first one is a survey paper by Nicolas Perrin, published in Transformation Groups in 2014. And the third one is by Jacopo Gandini. It is published in Chinese journal Acta Mathematica Sinica, English series of this journal. Actually, this is also notes of a lecture course of a school in Sanya in China, in the Yao Center, which took place in 2016. And the notes of this school were published in 2018 in this journal. So, and finally, I can give you a reference to my book, which is of more general scope. It is devoted to homogeneous spaces, not only spherical, but more general. But there is also some information about a spherical case in this book. And there are a lot of references. Quite complete list of references, at least at the state for the state of 2011. Of course, more works appeared since that time, but for that year, the list of references is more or less complete. So it is again a survey, but you can find some proofs also and some links to other papers. If you are interested to go deeper in this theory, you can use this survey as a starting point. Okay, so now we'll turn to examples. The first example will be the one which already appeared at the very first lecture. This is an example about plane conics. So in this example, we are considering the spherical homogeneous space Y0 of smooth conics in the projective plane. This space is spherical for the action, for instance, for the action of the group GL3. which acts on the projective plane by linear transform of variables of coordinates, and therefore it acts on the space of conics in the projective plane. We choose the standard Borel subgroup in G, consisting of upper triangular matrices and the standard maximal torus T, consisting of diagonal matrices. Of matrices, I just denoted by T of the form T1, T2, T3 on the diagonal, and 0 outside. Okay. So the character lattice of this Borel subgroup or maximal torus, whatever, is of rank 3. It has the basis, which I already denoted by epsilons, epsilon 1, epsilon 2, epsilon 3. This is the basis of this lattice over Z. And these basic characters, epsilon i's, are just diagonal entries of this matrix T. So in my notation, which I used previously, T to the power epsilon I, which is just the notation for the value of epsilon I at the element T, is by definition the ith diagonal entry of the matrix T. Okay, so this is my notation. So my aim is to compute the color data of this spherical homogeneous space and of some of its compactifications. There is a natural compactification of the variety of smooth conics in the projective space of all conics on the projective plane. So let me recall that we have the space of plane conics, and it can be of smooth conics, and it can be embedded in the space of all conics, which is just the projectivization of the space of symmetric 3x3 matrices. It is a 5-dimensional projective space, and the correspondence is as follows. So to each point, so the points of this projective space are symmetric matrices. I will denote such a matrix by Q. So Q is a symmetric matrix, 3x3. Sorry. Symmetric. The point in this projective space is given by this matrix considered up to a multiple. So these matrices define quadratic forms in homogeneous coordinates on P2, which give the equations, which are the equations of plane conics. The subset of smooth conics is given in this projective space by the non-degeneracy condition, so by the inequality that the determinant of this matrix Q is non-zero. Q is non-zero. Okay. Now let's consider the upper left corner minors, or if you like, the leading principal minors of such a matrix. These minors. These two minors, excuse me, draw better like this, and the determinant, the whole determinant of the matrix. So these minors, let me denote them by deltas. So delta K of Q is the determinant of the submatrix Qij, where Ij range from 1 to K. So K is 1, 2, or 3. This determinant is not a function on this projective space because it is a homogeneous polynomial in homogeneous coordinates on this projective space, which are just the matrix entries. It is not a function. It is rather a section of a line bundle on this projective space. So this line bundle, if you take delta K, this will be a homogeneous polynomial of degree K in projective coordinates. This means it is a section of the bundle O of K on the projective space. And this section is a B semi-invariant. If you act by a linear transform by a upper triangular linear transform of variables, then these minors will multiply by some scalars, which are the eigenweights. So the eigenweights, to compute the eigenweights, it suffices to multiply to make diagonal transform of variables. So, and it is easy to compute these eigenweights. They are, so eigenweights in my notation, the eigenweights are, so if you compute the eigenweight of delta K, it will be epsilon 1 plus etc. epsilon K taken twice. How to compute this? You just make a linear transform of variables given by this matrix. In terms of matrices, this means that you multiply the matrix Q by T on the left and by T transpose on the right. And of course, under this multiplication, the first minor will be multiplied by T1 square, the second one by T1 square, T2 square, and the whole determinant will be multiplied by T1, T2, T3 square. This exactly means that the eigenweight is this one in the additive notation for weights. So we have these sections of homogeneous bundles of line bundles over the projective space of all conics in P2. And if you consider the open B orbit, so if you consider the open B orbit, which I usually denote by Y upper node, it is given by non-vanishing of all these minors. The open B orbit is given by these inequalities. It is just the Gram-Schmidt orthogonalization. Orthogonalization. We already discussed this sometime on some of previous lectures. So it follows from the Gram-Schmidt orthogonalization process that if you have a quadratic form given by such a matrix with non-vanishing leading principal minors, then it can be put into the standard form. It can be transferred to the identity matrix by upper triangular change of variables. By the way, I see that I made a typo here, so here it should be 0, of course. I consider upper triangular matrices. Here it should be 0. So this gives us an open B orbit. And the complement of this open B orbit consists of three B-stable divisors. So the complement P5 without Y upper knot is the union of three B-stable prime divisors, D1, D2, D3. Well, these divisors are just the divisors of the sections delta K. So delta K, dk is the vanishing locus of delta K. It is the divisor of this section of O of K. The first two of these divisors are colors. They are B-stable, but not G-stable. And the third divisor, excuse me, I made another typo here. So here it is delta 3, D3. And the third divisor given by vanishing of the determinant of Q is G-stable. And there are no other B-stable divisors on P5. In particular, this means that there are only two colors. So the set of colors consists of D1 and D2. Thus, we have computed all colors. This is the first of our color data. Okay. Now we compute the weight lattice.
Hey, what?
Yes.
Oh, D3 is G-stable since. Oh, I see.
Because it is given by vanishing of the determinant, and this condition is G-stable.
Well, I still want to ask why is the eigenweights the sum of.
Well, let me repeat. I don't want to write anything. Let me just repeat in words. So first, it is clear. I hope it is clear that these sections are B semi-invariant. Yes. Because this is clear. Okay. Then, if you want to compute the weight of such a section, what you have to do? You have to make.
I forgot. I have to take determinant. Sorry. I was comparing the metric itself. I forgot.
No. You have to take determinant, and
yes, determinant. Yes, I see.
Now you get this. Yeah. Now you see why these are the weights. Okay. So let's turn to the weight lattice. To compute the weight lattice, I have to analyze B semi-invariant rational functions. Let's try to figure out what they are. So if you have a B semi-invariant rational function on the open orbit, for instance, but if you take a rational function, this doesn't matter. You may consider these functions on the open orbit or on this compactification, on this P5, this is the same. But let me, for convenience, consider. Let me start by considering a function, a rational function of an open orbit, which is B semi-invariant. But this function may be also considered as a rational function on this compactification of Y naught. So we may compute its divisor on P5, on this P5. The divisor of this function on P5 is, of course, a B-stable divisor. This implies that it is a linear combination with some integer coefficients of these dks. So these mi's are some integers. And this in turn implies that our function f the function, the irrational function on a projective space is determined by its divisor up to a multiple. So we can cook up such a function with this divisor. We can cook it up from these homogeneous polynomials delta k. Excuse me. Since the function f is determined by this divisor up to a multiple, it is proportional to the following: delta 1 to the power m1, delta 2 to the power m2 times delta 3 to the power m3. Because this product has the required divisor, this one on P5. But also you have to get a function. This product is just a ratio of sections of line bundles. So in order to have a true rational function, the total degree of this product should be 0. So we have a condition that m1 plus 2m2 plus 3m3 should be 0. Any function is a product of sections. Any function, any rational function which is B semi-invariant is a product of sections of line bundles corresponding to B stable prime divisors to some powers. And in order to have this product, and in order that this product gives us a rational function, we should have this condition. So all rational functions, all rational B semi-invariant functions up to a multiple are of this form. Now it is easy to deduce that any such function.
Hey, Professor.
Yes.
The divisor di belongs to y0 or belongs to P5?
To P5. We consider the divisors on P5. Y0 is an open subset in P5, and of course.
In the last page, I think di is you write. Oh, so the color should be D1.
D1 and D2 are colors. D1 and D2 are colors, and they intersect, of course. They intersect Y0. And D3 is G stable. It doesn't intersect Y0.
Oh, I mean, the colors should be the intersection of D1 and Y0, not D1 itself.
Oh, well, it depends on how you define colors. So when we discussed color data, we said something like that colors on different embeddings of a given homogeneous space are in a one-to-one correspondence. So this is a birational invariant. You may consider the color, a given color on any embedding of Y0 just by taking the closure. So essentially this doesn't make any essential difference because the valuation will be the same, everything will be the same. So here, I prefer to consider colors as divisors in here. So D1 and D2 are closed codimension 1 irreducible subvarieties in P5. But of course, if you intersect D1 and D2 with Y0, you will get colors on Y0. Okay?
So we consider the whole P5 as the acting space of G, right?
Exactly. This is a compactification of Y0. So Y0 is an open orbit in here. And here we have several orbits, in fact, 3 orbits given by the rank of Q. And it is a spherical variety containing Y0 as the open orbit. So we consider divisors on this compactification. But for colors, it doesn't matter. As I said, it doesn't matter which compactification to take, or even you may not compactify. You may consider the divisors on the homogeneous space Y0 itself. it doesn't matter, because what we are interested in valuations and respective vectors in the dual of the weight lattice, these VD bars, which give us the colored data. Okay?
I see.
Okay, so let's go on. As I said, any B semi-invariant rational function is of this form with this condition, up to a multiple. And now it is easy to see that any such function can be expressed as a product to some integer powers of the following two functions, which are the generators of the generators of the multiplicative group of B semi-invariant rational functions modulo scalars. We can take the following functions for the generators. So f1 equal to d1 square over d2, and f2 equal to d2 square over d1 d3. So I claim that any function of this form with this condition can be expressed as a product of f1 and f2 to some integer powers. It is an easy exercise to you to deduce. So this condition is essential, of course. So to deduce that any function of this kind is a product of this one to some power and this one to some power. And the eigenweights of this function, eigenweights are the following. Here we have the weight lambda 1, which is equal to 2 times epsilon 1 minus epsilon 2. And here we have lambda 2, which is equal to 2 times epsilon 2 minus epsilon 3. Just take the eigenweights of delta k's, these weights, and compute the weight of the numerator and subtract the weight of the denominator. In the additive notation, you have to multiply the eigenweight, for instance, of delta 1 by 2 and subtract the eigenweight of delta 2, and you get this. And similarly, you get this weight here. So these weights, lambda 1 and lambda 2, are the generators, give us the basis. So this is the basis . This is the basis of the weight lattice of my homogeneous space. So we have computed the weight lattice. The weight lattice here is of rank 2. And now let's consider the vectors corresponding to the B-stable divisors, d1, d2, d3. So let me denote such a vector by v sub k. So v sub k is v dk bar. And I want to compute these vectors. So how I do it? So the vector vk is defined by the following condition. Its pairing with lambda 1 and lambda 2 is equal to the vanishing orders of f1 or respectively f2 along the divisor dk. So for instance, if you take v1, then the pairing of this vector v1 with lambda 1 should be equal to the vanishing order of f1 along d1. This vanishing order is 2 because we have delta 1 square in the numerator of this fraction. So the pairing with lambda 1 is 2, and the pairing with lambda 2, with this one, is -1, because here delta 1 is in the denominator. So the pairing with lambda 1 is 2, the pairing with lambda 2 is -1, and it is easy to write down such a vector. So I will write it in terms of the basis of the dual basis of the character lattice of T, in terms of the dual basis of this one. So the dual basis vectors I will denote by stars. So this vector v1 will be epsilon 1 star minus epsilon 2 star over 2. It is easy to see that the pairing of v1 with lambda 1 is indeed 2, and the pairing of v1 with lambda 2 is indeed minus 1, as required. Well, in fact, I should be more precise here, because the character lattice lambda, the weight lattice lambda, is a sublattice in the weight lattice of the whole T, in the character lattice of T. So this one is of rank 3, and this one is of rank 2. Is isomorphic to Z to the 2. So lambda is a sublattice in lambda of T, and the dual lattice lambda star is the quotient of lambda T star. So when I write like this, I take vectors in the dual lattice of lambda of T, and I have to take the quotient. So for instance, this vector space E is the quotient space of the vector space spanned by the dual of lambda of T. The vector space E is the quotient space of the vector space spanned by epsilon 1 star and epsilon 2 star. But I can identify this quotient space with a subspace in E consisting of vectors whose coordinates sum up to 0, like here. So, and under this identification, I just can write these vectors in terms of this basis. So this is V1, and similarly, the other vectors V2 and V3 can be written like this. V2 is epsilon 2 star minus epsilon 3 star over 2, and V3 is minus epsilon 1 star minus epsilon 2 star plus 2 times epsilon 3 star over 6. So these three vectors have the desired pairings with lambda 1 and lambda 2, corresponding to vanishing orders of F1 and F2 along the divisors D1, D2, and D3. Okay, so maybe I should draw a picture describing this set of vectors. Let me do it here, like this. So we have, say, let it be, yeah, let me first draw the picture and then I will comment maybe. Okay, let it be like this. Here, let it be like this. Yeah, it is okay. So, and we have V3, which will be, I guess, somewhere here. So the vectors are these. So, for instance, this is V. V1. This is V2, And somewhere here we have V3. And also for your convenience, let me draw this epsilon1, epsilon2.
Professor.
Yeah.
So since V1 is in the quotient space of lambda t, the choice, the representation of V1 is not unique, right? We just choose one.
Yes. But if you require that the coordinates sum up to 0 as in all these cases, then this representation will be unique.
Oh, the sum of the coefficients in Vi of epsilon I star should be 0. Oh,
yes. Then such a presentation will be unique. So maybe for your convenience, excuse me, let me also draw the epsilon stars here. So to be precise, I think I should take like this. So well, I think yes, like this, something like this. Here. Oh, maybe let me skip this. So again, it is an exercise for you that the geometric picture. So assuming that this epsilon I stars give you an orthonormal basis of the three-dimensional vector space, then the geometric picture will be like this. So the angle here will be 120 degrees, and here it is the right angle. So the picture will be like this. Okay. So next, consider. So I'm interested also in the valuation code. But for this purpose, let me consider this embedding now. Let me consider this compactification and observe that this embedding of y naught into this projective space is a simple embedding. This is a simple spherical variety with a unique closed orbit. So the closed orbit here is given by matrices of rank 1. So the closed orbit y naught. No, not y naught. Excuse me. Y naught is the open orbit. Y1 is given by this condition that the rank of Q is equal to 1. And let me compute the colored cone corresponding to this closed orbit. So the colored cone is given by divisors, by vectors, is spanned by the vectors corresponding to prime bistable divisors.
Professor,
yes.
Closed orbit in what place?
Closed orbit in this compactification of y naught, which we consider.
Well, in P5, shouldn't the closed orbit be the zero orbit?
What do you mean by zero orbit?
No. There is no 0 point in P5.
Yes. Right? So the points of this guy are symmetric matrices. And the closed orbit is given by symmetric matrices of rank 1, the smallest possible rank. Okay?
Yes, but how do we know it is the only closed orbit?
Well, because we know all orbits actually. The classification of quadratic forms gives us.
I see. The orbit is the matrix with bounded rank. I see.
The orbits are matrices with fixed ranks, and the orbit closures are matrices with bounded ranks, and the smallest one will be of rank 1. Okay. Okay. So, the colored cone, the cone C sub y1, is spanned by the vectors corresponding to b-stable prime divisors containing the closed orbit. So the b-stable divisors are given by these equations. And the b-stable divisors containing the closed orbits, the orbit of matrices of rank 1, of course, these divisors are D2 and D3. If you have a matrix of rank 1, then these two minors vanish on this matrix. And this one does not necessarily vanish, because the matrix may have rank 1 and still non-zero, still non-zero thing here, non-zero matrix entry here. So the cone corresponding to y1 is spanned by the vectors v2 and v3, and the set of colors let me shift it a little bit, because here I have not enough space. Yeah. So the set of colors consists of a single color corresponding to the divisor to the color containing y1. This color is D2. So let me draw this cone somewhere here. For instance, so we have V2 and V3. This will be this cone. This cone, CY1. Okay. And we have computed the colored cone of this simple spherical embedding. Okay. And now, to compute the evaluation cone, we need yet another compactification of the open orbit. So let me turn to the next page. Yet another compactification, which we already considered at the very first lecture, is given by embedding y0 to the dual projective space. To the dual projective space, which I will denote also
Hey, Professor,
as...
I want to see the last page about
Yes.
Oh, I see. Thanks.
Okay. So the dual projective space, which I also denote as P5 star, it consists of conics in the dual projective plane. So this embedding is given, we already considered it at the very first lecture, this embedding is given by sending a smooth conic to the dual conic, which lies in the dual projective plane. And the dual conic, the points of the dual conic are tangent lines to the initial conic. So if the conic is smooth, then the dual one is also a smooth conic in here. And we obtain an embedding to this dual projective space on the matrix level. On the matrix level, this embedding is given by sending a conic corresponding to the matrix Q to the conic corresponding to the matrix Q inverse. This works for smooth conics, of course. Or the same thing, the conic corresponds to the adjoint matrix, Q check. The adjoint matrix differs from Q inverse by the determinant, by the multiple, which is the inverse of the determinant of Q, as you know, by the formula of the inverse matrix. So this gives you another compactification, another embedding. And actually, this projective space, this dual projective space, can be identified with the previous one, but with the twisted action of GL3. So the group GL3, my G, acts here in a twisted way. The twisting, yes.
About the last page, I think
Okay.
there are some. Well, I think dy1, the left, the right lower corner, dy1.
dy1, yes.
I think dy1 is the B orbit is the B stable orbit containing y.
No. Let me recall you the definition. dy1 is the set of colors containing the closed orbit. dy1 is the set of colors containing y1.
Yes, the set of color containing y1 should be d2 and d3, right? I don't see
exactly. But d3 is not a color. d3 corresponding to this vector is a g-stable divisor. The color is this one.
d2. I was thinking about you write d1. Oh, this is d2, right?
Yes, this is d2. Maybe it is not clearly written, but this is d2. Okay. So the action, as I said, this dual projective space can be identified with the initial projective space, just the space of symmetric 3x3 matrices, with the twisted action of GL3. The twisting is given by an automorphism of GL3, by an automorphism of G, taking a matrix G to G inverse transpose. Because if you think about, the action of G on the space of conics in the matrix language is given by sending a matrix Q to G inverse. Let me write it to the left. On the left. The action of G on the space of plane conics is given by sending a matrix Q to G inverse transpose times Q times G inverse. This is the action by linear change of variables, by linear transform of projective coordinates on the projective plane. So the matrix of the quadratic form is transformed in this way. And if Q is transformed in this way, then Q inverse, which is again a symmetric matrix 3x3, will be transformed in this way. G times Q times G transpose. So you may identify the dual space to this one, to the space, to the projectivization of the space of symmetric matrices, the initial one, but on which G acts not in this way, but in this way. So the action of G is twisted by this automorphism. And of course, this twisting does not preserve the Borel subgroup. This twisting sends the Borel subgroup of upper triangular matrices to lower triangular matrices because we take transpose.
Professor.
Yes.
I think the Q minus to the map to what the inverse matrix of what you write.
Yes, you are right. I have forgotten to put inverse. Thank you. I have forgotten to put inverse here, right? Okay. So under this twist, under this automorphism of G.
I don't mean. I'm not mean inverse on this. I mean inverse on the whole product, I think.
No, I mean that if Q is transformed in this way, then Q inverse is transformed in this way. If you take the inverse of this guy, you will get this, right?
The inverse of this guy.
The inverse of this guy will be this.
Oh, yes, I see.
Okay.
I see.
Okay.
But I still have a question. So, if you if you apply G to Q minus in the dual projective place, then I think you should left multiplicate by G inverse transpose, not G. How is this phenomenon happen?
Well, no. This space is just the symmetric. Well, I mean, if your projective plane is the projective.
I see. Since G acting on Q as G times Q times G, well, is it true?
Yes. This first formula is the formula for transformation of a quadratic form under the linear change of variables. The quadratic form given by the matrix Q. So this quadratic form is an element in the symmetric square of the dual of the three-dimensional vector space. So your projective plane is the projectivization of K3 of the three-dimensional vector space. And this quadratic form sits in the symmetric square of the dual space. So this duality produces this minus one power here. And this is how the matrix of this quadratic form transforms under the action of G on this projective plane or on the overlying vector space of dimension 3. This is how the matrix of the quadratic form transforms. And if you take the dual vector space, this will be the symmetric square of the initial vector space, not of its dual. And the matrix of G will be replaced by the matrix of the dual transform in the dual vector space. The matrix of the dual transform is this one.
I see. Thanks.
So, well, maybe some details, I'm skipping some details, but you can figure out all details by yourself. This is just from definition of the action. But let me continue. So the Borel subgroup of upper triangular matrices under this automorphism transforms to the opposite Borel subgroup of lower triangular matrices. And this opposite Borel subgroup preserves. So if you have the dual space, if you have this dual space, which I can identify with the initial space, because both of these spaces are represented by symmetric 3x3 matrices. But if I take a matrix in here, then under this lower triangular Borel subgroup, let me draw this matrix here. Okay, so under this lower triangular Borel subgroup, this one, the upper left corner minors will be no longer semi-invariant. Instead, the lower left corner minors will be semi-invariant. These minors will be semi-invariant. But if you want to come back to upper left corner minors, you have to rewrite the coordinates in the reverse order. So the third coordinate should be the first one, and so on. Equivalently, you can conjugate by the matrix which writes the basis in the opposite order. So the eigenweights, which we considered before, the weights epsilon 1, epsilon 2, and epsilon 3, under this automorphism, they will transform to the weights minus epsilon 1, minus epsilon 2, minus epsilon 3. Because when you apply, excuse me, minus epsilon 1, minus epsilon 2, minus epsilon 3. Because when you apply this automorphism to diagonal matrices, then you may not transpose, you just take inverse. So all matrix entries will be replaced by inverses, and this causes this -1 sign here. And after that, when you rewrite the coordinates in the opposite order, then this will transform the weights in the following way. So this sequence of weights will turn to this one, minus epsilon 3, minus epsilon 2, minus epsilon 1. So if we identify this dual compactification, this dual projective space with the initial one, with the twisted action of G, and consider the embedding of y naught in the twisted action under this twisted action, then all weights will transform in this way. And in particular, the vectors which we introduced here, v1, v2, and v3, will transform to the following vectors. So v1 and v2 will be interchanged. If you look at v1 and v2 here, and you replace epsilon 1 by minus epsilon 3, epsilon 2 by minus epsilon 2, and epsilon 3 by minus epsilon 1, then this will interchange these two vectors. And the vector v3 will transform to the following one. The vector v3 will be actually interchanged with the vector v4, which is the following, which is minus 2 epsilon 1 star plus epsilon 2 star plus epsilon 3 star. So the colors under this twisting will be interchanged, and the divisor D3 will become the divisor in this compactification, given by the same condition that the determinant is 0. But now, so let me write it here. So for the dual compactification, for the P5 star, the complement of
Professor,
yes.
V3 should map to V4.
It is just a notation. So under this transformation of weights, V3, which is here, which is written here, will map to this one, but I forgot to divide by 6. I'm sorry, divide by 6. To V4, which is which is this one. And the complement of the open B orbit in the dual compactification will be the union of the same colors, D1 and D2. You could say in a different order, and the divisor D4, the G-stable divisor corresponding to this vector V4. So VD4 bar is exactly V4. This means that so the closed orbit, the unique closed orbit, Y2, which is given again by the condition that the rank of a matrix here is 1. Because actually this is the same variety, but with the twisted action of G, I could say. So this the same closed orbit, but with the twisted action of G, we'll have the colored cone. We'll have the colored cone. Spanned now by the vectors V1 and V4. because these vectors correspond to the vectors v2 and v3 spanning the colored cone of the orbit y1 on the previous compactification on here without the twisting. So this cone v1 spanned by v1 and v4 and yes.
I still don't understand why epsilon 1 is transformed into minus epsilon 3.
Well, let me come back to this a minute later. Let me just finish, because otherwise I will never finish. I have to make a break already. I see the watch. So I will explain it. But let me finish here. So the set of colors, which previously was D2, now it is D1, because these two colors interchange under this twisting. And you can see this on the picture. So let me come back to the picture. So here we have another vector, v4, which is this one. I think it is, well, let me. Yeah, I think it should be something like this. Is orthogonal perpendicular to v2 now. Okay, so this vector will be v4. V4, and the cone, the colored cone now will be this one, spanned by v4 and v1, this one. So this will be C comma y2. Yeah.
I think v4 is the sum of v4 and v3 is 0. I think if you write that.
No. It's not true. So just look at these vectors. It is not true that their sum is 0.
Then how can we write v4 to be epsilon 1 star, the sum of
v4 is this one.
And
v3 is this one.
I forgot that we reverse.
Yeah. We reverse the ordering. So we get the cone for the another compactification. It is this one. And now let me finish by saying that having these two colored cones, we also know that both of these varieties are complete. And by the criterion of completeness, so let me write it here. So it follows from the completeness of both compactifications, and from the criterion of completeness, that both cones CY1 and CY2 contain the evaluation cone. And on the other hand, the evaluation cone contains the vectors V1 and V2. So let's look at the picture. Coming back to this picture, let's look here. So both of these cones cover the evaluation cone. And on the other side, these two vectors, so their intersection covers the evaluation cone. So this intersection covers the evaluation cone. And these two vectors, V3 and V4, belong to the evaluation cone. This means that the evaluation cone is exactly this intersection. So the evaluation cone, this implies that the evaluation cone is exactly the intersection of these two cones. And it is the cone spanned by these two vectors, not V1, I'm sorry, not V1 and V2, V3 and V4, excuse me. I'm making too many mistakes. Sorry for that. V3 and V4. So coming back to this picture, we see that the evaluation cone is exactly this intersection. So let me brush it in green, as I usually do. This is exactly the valuation cone, and finally we have computed all colored data. And now finally I can finish the first half of my lecture. So sorry for this, for going out of my time for the first half of the lecture. Let me stop here, and I'm ready to answer questions.
So we reverse the order of epsilon I star because the invariant minors is in the reverse order, right?
Exactly, because we want to come back to the initial Borel subgroup. Because we are interested in colors corresponding in colors in whatever we have in B semi-invariant functions corresponding to the initial choice of the Borel subgroup. All Borel subgroups are conjugate, so it does not essentially matter which of them to choose, because the respective data for the other Borel subgroup are in a bijection with those for the initial one. But since we have fixed the Borel subgroup here, this automorphism destroys it. It takes us to another Borel subgroup. And we want to come back here. So for this purpose, we have to apply conjugation. We conjugate by a matrix rewriting the basis vectors in the reverse order, so that the lower left corner minors become again the upper left corner minors. And this is why here we reverse the order of weights, like this. Okay?
Well, so D3 and D4 are G-invariant
Exactly.
divisors.
Right.
So they belong to the valuation cone. I see.
Yeah. So the point, let me repeat this idea. The point here is that we know two compactifications. The compactification, two simple compactifications. The first one corresponding to this cone, and the second one corresponding to this cone. We know the colored cones. So we know the colors, this and this, and we know the G-stable divisors on these compactifications. They correspond to this vector and this vector. So we know some vectors in the valuation cone, this and this. And we know that these cones cover the valuation cone. And this is a restriction strong enough to determine the valuation cone uniquely, because since it is covered by this cone and by this cone, it is covered by their intersection. And on the other hand, these vectors belong to the valuation cone, this we know, and they span this intersection. Therefore, the valuation cone coincides with the intersection of these two cones. This is the way how to compute the valuation cone in this example. So in a sense, it is indirect, because the direct way to compute the valuation cone is complicated. As you remember, we computed the tails in the coordinate algebra. Well, this works for affine homogeneous spaces or quasi-affine. In the general case, we have to take the affine cone and then take the coordinate algebra. So to compute the tails, we have to decompose simple G submodules in the coordinate algebra, the products of simple G submodules in coordinate algebra into irreducibles. This is a complicated thing. It is usually beyond control. It is very hard to compute. So the more practical way to compute the valuation cone is to use this completeness criterion. So completeness criterion.
I see.
Yeah.
So, Professor, the criterion that the V3 is belong to the cone of V1 and V4 is by pure calculation, right? You can't denote this only by non-numerical analysis.
Yeah, I mean, we get some vectors in the valuation cone, these two, V3 and V4, just by producing explicit compactification, say in geometric terms.
I'm not. I mean, to determine that V3 is belong to the cone of Y2. We have to write down what V3 exactly in the coordinate.
Well, I mean, so V3 indeed belongs to this valuation cone, but it is not in the colored data of Y2 because
I know
cone,
it is not in the color data of Y2. I mean,
yeah.
the V3 belongs to the colored cone. In order to prove that V3 belongs to the colored cone, we have to write down what V3 exactly is, right?
Yes, of course.
So we still need linear algebra to determine that V3 belongs to the cone.
Yeah, of course we need linear algebra, but linear algebra, I mean, we need to know all these weights, all these things, but this is much easier than decomposing products of irreducible submodules. This is just a linear algebra, and the second problem is a problem in the representation theory. So it is much more complicated. So here we avoid these difficulties by indirect arguments. We did not compute the whole cone. We did not give this cone by inequalities, but instead we picked some vectors. We proved that some vectors belong to this cone, and we obtained an upper estimate, an estimate from above for this cone, that it is covered in this by this one and by this one. And finally, from these estimates, we obtained the exact shape of this valuation cone. This is how this argument goes. So, more questions? Well, I think we still have a couple of minutes. So let me turn off my microphone, but I'm here. So if you have questions, please ask. Well, okay, I think we can continue. So this example gives an idea about how to compute the colored data of a spherical homogeneous space in general. One finds several nice explicit geometric models and compactifications of a given spherical homogeneous space. Analyzing their structure geometrically, one finds the colors and boundary G-stable divisors on these compactifications. And this information is used to describe the B semi-invariant rational functions and the weight lattice. To find the valuation cone, one can use that it is covered by the fan of each of these explicitly known compactifications. And also that several vectors of the valuation cone coming from G-stable divisors on these compactifications are already known. So as in this example, we know several vectors. The cone spanned by these vectors gives an estimate for the valuation cone from below. And the estimate from above is given by the fact, by the completeness criterion, that this valuation cone is covered by the fan of each of the compactifications which we have explicitly computed. So if these compactifications are carefully chosen, and we have chosen enough of them, sufficiently many of them, then this data will suffice to describe the valuation cone in whole. So let me give you some exercises to try this idea in other examples. So the first exercise. So recall that we also have the variety of complete conics. Recall from the very first lecture that we have the variety of complete conics. Which is the closure of the homogeneous space of smooth conics embedded diagonally in the product of the above compactifications P5 and P5 star, which we considered before in this example. And an exercise is to prove. So let me write like this. So the first part is to prove that X is simple. That X is a simple spherical variety with a unique closed orbit. This can be done geometrically. And the second part is to compute the colored cone. Well, let me write it like here, like this. Prove that X is simple with a closed orbit denoted by Y. And the second exercise, the second part is to compute the colored cone of this closed orbit, the colored cone of this simple spherical variety. And similar exercises concern other spherical varieties. Exercise 2. So let V denote the four-dimensional symplectic vector space. Four-dimensional symplectic vector space. With symplectic form denoted by omega. And I consider the projectivization of this symplectic vector space. It is three-dimensional. And for the group G, I take the group SP4. The group of symplectic transformations of this vector space corresponding to the symplectic form omega, which is just SP4. Now y naught will be the set of pairs of points P1, P2 sitting in the double of this projective space P3 cross P3, such that these points correspond to some vectors in the overlying vector space, and the linear span of these vectors is a two-dimensional subspace in V, on which the symplectic form is non-degenerate.
A symplectic subspace, right?
Excuse me? A symplectic subspace, yeah, exactly. A symplectic subspace. So the first part is to prove that y naught is a G-spherical homogeneous space spherical homogeneous space for the action of G, and the second part is to compute the colored data of this homogeneous, of this spherical homogeneous space. Compute.
Professor, what is the pros of group of a symplectic group?
Well, if you choose the symplectic form having the matrix with plus minus 1 on the secondary diagonal, then the Borel subgroup will consist of upper triangular symplectic matrices. But of course, yeah. If the symplectic form is chosen in such a way that its matrix is has something on the secondary diagonal and zeros outside, then the Borel subgroup can be chosen to be consisting of all upper triangular matrices sitting in SP4, sitting in the symplectic group. But of course, it is better to consult some books, some reference books in algebraic groups to get deeper into the structure of symplectic group. For instance, in Humphrey's book, or in Winberg and Onishik and Winberg's book, which the references which I gave some time before. Because of course you have to know something about the structure of the symplectic group to solve this exercise. Okay, so so to compute the colored data, the second part of this exercise is to compute the colored data. And now let me give yet another exercise, just to make things more various. Exercise exercise 3. Now let me consider the homogeneous space y naught, which is G over H, where G is just G2, and H consists of the matrices of this form. And the parts of this exercise are the same. So the first part is to prove that y naught is a spherical homogeneous space for the action of G. And the second part is to compute the colored data. So the idea in all these exercises is the same as in the example. So you construct an explicit geometric model. For instance, here you already have such a model. Yeah, and of course here also. Here you have already constructed colored data. You have only to prove these two things and to compute the colored cone. But in the other two exercises, you have first to construct a geometric model for this homogeneous space. Here it is already given. You have to construct several compactifications, several nice geometrically given, several nice compactifications given just geometrically in an explicit way, to compute divisors, B-stable divisors, the corresponding vectors in the vector space E, and so on. And then to find evaluation cone by the same method as in the previous example. So try these exercises, and if you will succeed to solve them, then you may be sure that you got the idea of these computations. Okay, well, for the next example, so this was our first example in which we so several examples, the first one of which we computed, and the other examples are left as exercises for you. And for the next example, we consider toric varieties. Toric varieties. So what is a toric variety? By definition, well, at least one of the possible definitions, by definition, a toric variety is the same as spherical variety. Spherical, say X, spherical for the action of an algebraic torus. So in this case, G is an algebraic torus, which I denote by T, because it coincides with the maximal torus of G in this case. So G and the maximal torus in G are the same. Toric varieties can be defined as spherical varieties for tori actions. The class of toric varieties is maybe most explicit and easily accessible among general spherical varieties. Their theory deserves maybe a separate lecture course, but we just explain how toric varieties fit in the general picture of spherical varieties. Let me start with the open orbit. Which I denote as usual by y0. It is an orbit for the torus T, an orbit of some point, say y small naught, and therefore it can be described as a quotient space T over the stabilizer of y0. But since T is abelian, an algebraic torus is an abelian group, this stabilizer acts trivially on the variety X just because the stabilizers of all points in the open orbit are conjugate. But since the group is abelian, there is no conjugation. The stabilizers of all points in the open orbit are just the same. So this stabilizer acts trivially on the open orbit. And since this orbit is dense in X, it also acts trivially on X, X. So this stabilizer is just the ineffectivity kernel for this action, for the action of T. And this means that we can mod out this kernel. So we can replace T by the quotient group T over T y0, which is again an algebraic torus. The quotient group of an algebraic torus is still an algebraic torus. And by this replacement, we may assume that the stabilizer is trivial.
Well, the stabilizer is also an algebraic group, right?
Of course. It is an algebraic subgroup in the algebraic torus T.
So the quotient is again an algebraic torus, right?
Yes, the quotient group of an algebraic torus is always an algebraic torus. This is a standard fact in the theory of algebraic groups, which, by the way, we already mentioned sometime before. I don't remember when, but sometime before we mentioned this fact. So we may assume that the stabilizer is trivial, and this means that the orbit.
Professor, the open orbit is the open G orbit or open B orbit.
Well, in this case, it is all the same. G and B and T are the same group. This is a very nice situation in which it doesn't matter which group you mention. All these groups are the same. Because if your G is an algebraic torus, it coincides with its Borel subgroup, and with the maximal torus, it coincides with all the other groups. Okay? So in this case, the orbit Y0 can be identified with the torus T itself, on which it acts, so T acts on itself by left multiplication. Well, left or right, this doesn't matter because the group is abelian, but let me, for compatibility with more general situation, let me write it as left multiplication. So the open orbit is T itself acted on itself by left multiplication. And we shall always adopt this convention for the sequel. So we assume that a T acts effectively. This means that the stabilizer of the open orbit is trivial. So we adopt this convention. Okay, let us describe the color data for toric varieties, because the color data are the things which allow us to study toric varieties, different toric varieties containing a given orbit, a given torus, and so on. So let me turn to the next page. First of all, as I already said, in this case, the Borel subgroup B coincides with the acting group T. So we can even write like this. B equals G equals T. All these groups are the same. And in particular, this means that there are no colors. The set of colors is empty. Because what are colors? Colors are B-stable divisors, B-stable prime divisors, which are not G-stable. In this case, this cannot happen. So B and G is the same. So there are any B-stable divisor is at the same time G-stable. There are no colors. This is the first observation. Next, what about B semi-invariant functions and the weight lattice? Well, if you take any semi-invariant function of some eigenweight lambda and compute it at a point of the open orbit is just the torus T, so we compute it at an element of T, then it is the same as T to the inverse of lambda times the value at the unity point. Because, well, just by definition, because when you act when you act on a function by an element of a torus, you act on the argument of this function by T inverse. This means, well, when you start from the identity element and act by T inverse, you get your function is multiplied by T to the power lambda, by the value of lambda at this element T in this exponential notation. But here you write T, not T inverse. So this means that when you act on an argument of a semi-invariant function by T, then it is multiplied by the value of lambda at T inverse. This is this value. So essentially, any B semi-invariant function is proportional to a character. Is proportional to a character of a torus, of our torus. And what are the characters? What are the characters of tori? The characters are just Laurent monomials. Let me write it like this: T1 to the power minus L1, etc. Tn to the power L minus Ln, where T1, Tn T1, Tn are coordinates on T. For instance, if your T is realized as the group of diagonal matrices of size n by n, then T1, Tn are just diagonal entries. And all characters are just Laurent monomials in these coordinates. So these exponents are just coefficients in the decomposition of the character lambda in terms of basis characters. So we can write that lambda is the sum L1 epsilon 1 plus etc. plus Ln epsilon n, where these Li's are integers, and epsilon 1, epsilon n are basis characters, which we already have seen in the first example in this lecture. So let me write again that these characters just take the value of a character epsilon I on an element T is given by the ith coordinate. So in terms of this decomposition, we have exactly that the value of minus lambda, the inverse character minus lambda at the element T is given by this Laurent monomial. So all characters all semi-invariant functions are proportional to characters, and vice versa. Any character is a semi-invariant function on the torus. So this means that the weight lattice in this case, weight lattice, is just the character lattice of the torus. And the basis, it is a lattice of rank n, and the basis of this lattice is given by these epsilon i's. So we have computed colors, we have computed the weight lattice. What about the evaluation call?
So this process gives us B semi-invariant functions for any character lambda, right?
Right. This is what I have said. Any character is a B semi-invariant function on a torus. So the weight lattice is just the lattice of all characters, and epsilon 1, epsilon n is the basis of this lattice. Now, the open B orbit here is the same as the open G orbit. It is just our torus T. It is an affine variety, and the coordinate algebra of this variety is just the ring of Laurent polynomials in these coordinates T1, etc., Tn. Okay. This ring can also be written, maybe, let me put it on the next line. Here. This ring can also be written as the direct sum of one-dimensional subspaces spanned by all semi-invariant functions. So where lambda ranges over the weight lattice. Because any Laurent polynomial is just a sum of Laurent monomials, and any Laurent monomial is a character. And also all semi-invariant functions, are Laurent monomials, are characters, that is Laurent monomials up to a multiple. So we have this decomposition. In other words, the coordinate algebra of T is just the group algebra of the weight lattice. Because when you multiply the characters, the semi-invariant functions, their weights add up. And we get a semi-group algebra of the weight lattice. And at the same time also, these summands are nothing but irreducible T submodules in the coordinate algebra of highest weight lambda. In this case, all these irreducible submodules are one-dimensional. The representations of an algebraic torus are always one-dimensional. So in our previous notation, we can write these one-dimensional vector spaces as K of T sub lambda in brackets. This is our notation for the unique irreducible submodule of highest weight lambda in something, in the coordinate algebra of an affine spherical variety, for instance. Okay? When you multiply any two of such submodules, so when you multiply K of T lambda with K of T mu, essentially you multiply characters. And in the additive notation, you get again a character which is just the sum of lambda and mu. So this product space is just K of T sub lambda plus mu. And this means that there are no tails. Recall that tails are vectors which we have to subtract from this sum of highest weights to obtain all other irreducible summands in this product. But for the algebraic torus case, the product of two irreducible summands is just a single irreducible summand. There are no tails. And also, let me recall that tails give us inequalities, give us linear inequalities defining the evaluation cone. Since there are no tails, there are no inequalities defining the evaluation cone. And this means that the evaluation cone is the whole vector space E, spanned by the dual of the weight lattice. So the evaluation cone for the torus, for toric varieties, is just the whole vector space spanned by the dual of the highest weight of the weight lattice. So we have computed all colored data for the torus as a spherical homogeneous space. But let me elaborate a little bit more, since I have yet 6 minutes left for the lecture. Let me elaborate a little bit more, because in the toric case, many things become more explicit than in the general spherical case. So for any, regarding invariant valuations, for any vector v in the vector space E, we can construct a T-invariant valuation quite explicitly.
Professor, I still can't understand why no tails implies the graduation cone in the whole space.
You have to look back in the notes of the lecture.
Well, I look back. I think no tails. Tails. The difference of lambda plus mu and the other character is the sum of positive roots. I see we have proved this. But
and also we have proved when we discussed the evaluation cone, we have proved that each tail gives us a linear inequality on the evaluation vector. And all these inequalities define the evaluation cone. So the evaluation cone in general is defined by linear inequalities coming from tails.
Oh, I see that. Yes.
So if we have no tails, we have no inequalities, and any vector in the vector space E belongs to the evaluation cone. A very simple argument. Okay? Okay, so let me speak a little bit more about T-invariant valuations. So for any vector V in the vector space E, we can explicitly describe the T-invariant valuation as follows. So if you have any function on T, which can be expressed as a linear combination of characters of Laurent monomials, so a sum over sum I of coefficients Ci times f lambda I, where the notation is the same as before. So I take only those summands for which the coefficients are non-zero. If we have such a decomposition, then actually we have computed on some of the previous lectures when we discussed general G-invariant valuations on arbitrary spherical varieties, that in this case, the value of the respective valuation at f is given by the minimum of the pairings of V, of the vector V, of this vector V in E, with all weights lambda I. This formula was obtained before. Yeah. But if V is a lattice vector, so V is a vector in this vector space E, but if V is a lattice vector, a vector in lambda star, then so of course any vector is proportional to a vector in V in lambda star. Any vector in E is proportional with some positive multiple to a vector in here. So essentially, if we are interested in invariant valuations, we may consider only lattice vectors. And if V is a lattice vector, then this description of the corresponding valuation can be made more geometric in the following way. So any lattice vector defines a one-parameter subgroup in the torus T. A one-parameter subgroup, multiplicative one-parameter subgroup, is a homomorphism from K cross, from the one-dimensional torus to T. So the notation for this homomorphism is a parameter, a multiplicative parameter S maps to an element which I denote S to the power V. So I already used this notation. This in particular means that if we compute the function f from above at this element S to the power V, then we get the following. We get the sum over all i's Ci times Now we have to take the value of this character, f lambda I. F lambda I, for f lambda I, we can take this character, t to the power minus lambda I. And if we substitute t equal to s to the power v, then we get s to the power minus the pairing of v and lambda I. So if you substitute a one-parameter subgroup in each Laurent monomial in n variables, you will get a Laurent monomial in a single variable, in a variable s. And now, what is the value of our evaluation v at the function f? The value is given by this formula. So we have to take the minimum of these pairings. The minimum of these pairings correspond to the maximum of these pairings, which are the exponents in here. Or if you like, you can take S inverse for the variable here. And so you get the minimum of the degrees, of the monomials here with respect to S inverse. This minimum of the degrees with respect to S inverse is nothing but the vanishing order of this function f of S to the v at infinity, when S equals to infinity. So this function f of S to the v is a function on k star, on k cross. You may consider it as a rational function on the projective line. And this value is exactly the vanishing order of this function at infinity. So geometrically, you may, if you want to compute evaluation corresponding to a lattice vector, if you want to compute evaluation corresponding to a lattice vector, you have to restrict functions on this one parameter subgroup.
We have easier calculation for lattice vector, right?
Well, in a sense, I would say it is easier because this is quite easy. This formula is very easy. I would say this calculation is more geometric. It describes evaluation in geometric terms. So what you have your torus T. So here is somewhere here is the unity element, of course. And you have your one parameter subgroup. You have this curve S to the v, depending on a multiplicative parameter S. And you have to take, you have to tend S to infinity. And if you are interested in this value, you have to restrict your function f on this curve and compute the order at infinity. Okay, so this gives some geometric flavor to these invariant valuations. We'll discuss it in more details maybe at the beginning of the next lecture, because I want to say something more. We have computed colored data, but I want to say something more about toric varieties since they are most explicit and most simple structure in a sense among general spherical varieties. So I want to say some more words about the structure of toric varieties at the beginning of the next lecture. And now let me stop. Thank you for your attention, and please go ahead with your questions if you still have any questions.
Well,
Yeah.
Oh no. Oh, I know what is the oh no, the one parameter subgroup is determined by V. Oh, I see.
Yeah, actually, this notation, we already use this notation. So maybe to make it, to facilitate the understanding for you, let me recall somewhere here that if V is expressed as some linear combination K1 epsilon 1 star plus etc. plus Kn epsilon n star, where epsilon 1 star, epsilon ln star are, of course, the dual basis vectors, to these basis vectors of lambda. And the dual basis vectors in lambda star, I also denote them by star. So if V is expressed as a linear combination of these basis vectors, then actually what is S to the power V? S to the power V is an element in T, which is a tuple of coordinates. And these coordinates are S to the power K1, etc., S to the power Kn. Okay? But this expression, of course, depends on the choice of the basis, and this notation is independent of the basis. So more questions? Well, it seems that there are no questions so far, right? Anyway, feel free to write me on email should you have any questions further. But if there are no more questions at the moment, then maybe I can stop sharing the whiteboard. And we'll continue on Wednesday. We'll spend some more time discussing toric varieties and then go to further examples and constructions. So now essentially we move from general